Okay, hello. My name is Fabian Renn Giles, and I'll be talking about reflection without the reflection technical standard. I've been talking a lot these days, and I had a cold last week, so if I need to clear my voice, I apologize in advance. And I'll try to speak a bit softly, and I might have to drink a few times in between. So I apologize for that in advance. Anyway, why without the reflection technical specification? And that's because official reflection support is still a long time away. There was a reflection technical specification that was based much on meta-type template programming, and that's been considered a bit outdated. We have const-eval now, and so they're reworking that reflection technical specification, so it won't make it into C++ 23. Experimental versions, I've been told, may be available by 2023, but maybe not. Who knows? So we need to deal with what we have right now. So this talk is about reflection techniques that you can use today with current C++ standards. I'm also not going to talk about tooling. There's many ways you can get reflection today by using stuff like GCC XML or libclang. This is not what this is about. This is just inside of C++ with C++ compliant code. I'm actually not at all a C++ reflection expert. By all means, I usually do talks on real-time programming and log-free programming. But I love reflection talks. And I haven't really seen a good summary of all the reflection techniques that are out there in one talk. So I thought I might try to change that. Why do I love reflection talks? I always go to every conference, I go to a reflection talk, and I try to ask myself why I actually do this. And I think it has several reasons. One is, usually in the title already, you already understand what the goal is, right? You say, I want to reflect on the types of a struct, right? Every decent C++ developer knows what that means, what the goal is. But usually when you hear something like that, you immediately think it's impossible, because C++ was not made for reflection in mind, right? Reflecting on the types of the members of a struct, how do you do that? It just can't be. So every time I read a title like that, I'm intrigued to go there because I think the author must be wrong and must have made a mistake. But it turns out they're always right. But they use some really fun and pure genius solutions. And so I'm in there and I'm just smiling away all the time. These are my favorite talks. And looking back at all the conferences I went to, and I looked at my schedules because I always write them down and take notes, on every reflection talk, I've learned something really new that I didn't know before. And it's usually because, I think reflection talks use some of the most advanced C++ features. So I'm hoping that today you'll learn some new features that you might not have known about before. And to keep this fun and short, I want to structure this whole talk as little quiz questions. And if you're like me, I'm always like, no, this can't be possible. This can't be done with C++, and maybe you'll be surprised that it can be done with C++. So the first question, very, very simple question is, can we check if a type is a pointer or not at compile time without the STL, right? With the STL, it would be simple. There's std is pointer. Without the STL, with only C++ compliant code. Who thinks in this room that it can be done? And if you raise your hand, please also have a rough idea of how it could be done. I mean, I won't ask you, but okay, we have a few. This introduces the first reflection technique, which is template function specialization. So that's really, really easy. You create a templated struct. Up here is pointer. And for any type name t, that struct will always have a member value that's always false. It doesn't matter which t you put in there. So if I would leave the code as is, then this is pointer down here would print false. But now I add a template specialization of this struct, and I tell the compiler to consider this struct if the type matches that pattern, right? So that's super, super easy. So now it will consider this struct, and the value will be true if it matches that pattern. So if I look down here, that int star matches that pattern, so this prints true now. Can anybody see what's wrong with this code? And just shout out.
Well, you don't consider smart pointers?
Okay, right. Okay, this is pointer is not supposed to consider smart pointers, but that's a very good point. Yeah, I don't consider smart pointers. Anything else? The CV qualifiers are missing, right? So I would need to add const volatile. Otherwise, if my int star down there would be a const int star, it wouldn't work. So that's a very, very simple reflection technique that you can use. Just another example, instead of is pointer, we now have is array. Again, we have a struct, which for any type just returns false. But now we specialize this, and if the compiler can match this pattern here, which it could for a raw array, then the value will be true. So yeah, that's very, very simple technique. A related reflection technique is template argument deduction, which you can use, for example, to figure out at compile time the length of a raw array. How do we do this? We have a function declaration up here called array length helper, and it takes the non-type template parameter n. And then we have this global const extra array length variable, which just creates an instance of t here and passes it to that function. So if we want to check the length of a raw array of integers, of 5 integers, and then we're creating an instance of those 5 integers, and we're trying to pass it in here. The compiler will do template argument deduction, will deduce the template non-type template argument for us, this n, and then we encode the n in the return type of that function, so that down here we can, with decal type, figure out what type this function would actually return and get its value. So this is how you would get the length of an array, and I always find this really funny because we are sort of abusing function declarations, because we have a function declaration but we don't have a body anywhere, and we don't need a body, right? We're just using the function declaration to sort of use template argument deduction. Okay, next question for the room. Can we check if a type is polymorphic or not? Again, without the STL, only C++ compliant code.
Do you mean if it's derived class?
No, if it's polymorphic, so if it has virtual methods, for example, yeah, or an abstract pure virtual class, something like that, and anything that has virtual methods. What do people think? Is it possible? So raise your hand if you think it's possible. Okay, does anybody want to throw in the technique that we would probably use to do this?
I think like making a child class that derives from it that has a virtual and see if it's larger.
Ooh, that's a really good question. That might work. I haven't thought of that, yeah. That's a really good one, yeah. I have to think about that. So the technique that you would usually use, and you use for a lot of reflection, I think most of the more complex reflection you'll be using SFINAE, right? Substitution failure is not an error. And probably all of this in the room know what SFINAE is, but just as a quick recap, let's say I want to write a function called safeGet, which takes a raw array again and an index, and this function checks that the index is in bounds, right? So that we don't return out of bounds element. And you could imagine some code using that function like this here. And then one day we want to write an overload, though. We want to also use the same safeGet for a container. So we write a container version, but now we have a problem. If we still have this same safeGet here, the compiler will look at the overloads that we have, and it's now being passed a raw array of 5 integers. So it's going to consider this overload here, and it's going to say, oh yeah, I can deduce, I'm going to try to deduce this type name. It's a raw integer of 5, so let me substitute that in. But when we do that, right, we get ill-formed code here, right? Because int5 is not a namespace or struct. That's the compiler error we'd normally get. But due to SFINAE, substitution failure is not an error. We don't get any compiler diagnostics. The only thing the compiler will do is ignore that overload completely, so that only one overload remains. So that's what SFINAE is. And we can use this for reflection because we can write a function that at compile time, this check expression, which will check any expression for us involving t, and checking if that, at compile time, if that expression involving t is ill-formed or well-formed. So how do we do this? we write a function check expression that for any arguments just always returns false. Then we write an overload for this, which again is check expression, takes a single argument of type size t, and then we put our expression involving t, we put in there. And if it's well-formed, then that overload will be considered, and it always takes a higher priority than the ... one. So it would always use that overload if it's well-formed. If it's ill-formed, SFINAE will ignore that overload and only use the second one. So this is a really cool way to check if an expression at compile time is well-formed or ill-formed. And that's, of course, super powerful because we can basically reflect on, does this thing produce a compile error or not? And the reason we have the size of is it makes it more flexible because in the size of, size of can take two types of arguments. Either it can take types, but it can also take, values or instances. So that's why it's more flexible to put a size of here. Our goal is to find is polymorphic, right? So what do we want? We want an expression which is only ever well-formed if T is polymorphic. So for the room, what expression is only ever well-formed? Like what do you think might be involved in this? Overload. Any other idea? What's something we typically do with polymorphic types? Yeah, casting, right? So dynamic casting, all right? So we want an expression to involve that has some kind of dynamic cast in it. But now comes the harder question, what should new type be? So we have some expression involving T, let's say it's T star or T ref, but we want the dynamic cast to some new type, and it should only work if it's polymorphic. Anybody have any idea what new type could be? Ooh, good. This is something I never knew. So this is something I only learned during a post. So that's very good. Yeah, it's actually void star. So you need to look at the standard to really figure this out because I've never used it before in my life, and I don't know what the use case really is for this. But so let's look at what new type can be when you're using a dynamic cast. If we look at the standard, option number one is that the expression, so in the rounded brackets of dynamic cast, is exactly the target type, new type, right? But it says, the C++ standard, it says it's exactly the same as static cast. So this is not good because it nowhere says that our expression will be ill-formed if it's not polymorphic, right? This works for any type, right? If you're casting between something that is expression of T and you're casting it to T, that works for any expression. So we can't use this.
Well, type up itself.
Again?
Dynamic cast it to itself.
Yeah, but this is exactly that. This is exactly this point. If you dynamic cast it to yourself, I didn't know this either. I thought it would be ill-formed if it's not polymorphic, but it turns out that the compiler couldn't just replace that with a static cast. And the static cast works if it's polymorphic or not. It always works. And so that's not good because we want it to not work when it's not polymorphic. The second thing the standard says is something about null pointers that we don't care. We don't have a null pointer here, right? We have T. So we can't use that. The third thing is that when the new type is a base class of T, right? So imagine T is child, and the new type, the target type is base. Then it says again, this can be performed by a static cast as well. Nowhere does the standard mention it needs to be a polymorphic type. So again, we have the same problem, is that it's never ill-formed. So we can't use that. And then we have the canonical case of dynamic cast, is where you cast to a child. That's the normal canonical case of dynamic cast. That's how we normally in day-to-day code would use dynamic cast. And here, the standard does require it being a polymorphic type. So this is good. The problem is, where do we get new type from? We need some kind of child type. The user is only giving us T, right? So we can't really use it. But then there's this last point in the standard, which I've never knew. If you cast to void star, and the type is polymorphic, the result is the pointer to the most derived type by the expression. So who knew in this room that when you dynamic cast a void star, it actually casts to the most derived type that your polymorphic type can be? So we have one person who knew that. Anybody else? Okay, so I told you learned something new in reflection talk, so yeah.
So it's a type. So if you decal type on that, it wouldn't be void, so it would be whatever the
Exactly. Yeah. Crazy.
That's actually quite
Yeah, yeah. It is. It's pretty powerful.
Is the type is polymorphic, but there's no more derived object.
Then it will return itself. It would return.
It still
Right.
requires it to be polymorphic.
Yeah, it still requires it to be polymorphic. Yeah. So the expression you would write here is dynamic cast void star, and then just the decal val of t star. And I know this is right because Clang's STL uses this, so it can't be that bad.
I'm not sure it would work on Visual Studio.
Okay.
Actually, I'll shut up. Sorry.
Mm-hmm.
I don't think that's possible.
Okay. I mean, yeah, the STL uses it, so interesting. Okay, let's. So you don't think it's standard compliant?
I need to think about it. Sorry.
I mean, I have time in this talk, so yeah. So next question: who thinks after seeing this, that we can check if a type is a struct or a class type at reflection at compile time? Nobody else? Just one person? Two? Okay. So we're going to use the same technique. We're going to use SFINAE again. Which expression do we want to check to see if it's?
you can have a member pointer, isn't it?
Perfect. We want to do a member pointer. Very, very nice. Yeah, we put in a member pointer there, right? Because only if T is a struct or a class type will this work. And it doesn't matter if T actually has a member of type int, right? It's still well formed even if T didn't have a member int. As long as T is a struct or a class type, it will work. There's one problem. What's the problem?
I thought that you want to differentiate between struct and class.
What?
You don't want to differentiate.
No. We don't. We just want to see if it's a struct or a class. It doesn't matter if it's struct or class, right? I mean, if it's does any. Sorry? No, that's not it. No. No, that's not the problem. I think because it only needs to be well-formed or ill-formed, it doesn't matter if it's actually possible to do that with T, right? It could be that T has no members, for example. It just has to not be ill-formed code. So this is actually using the STL. The thing is that unions you can also bind to union members. So you might want to go one more. Instead of doing binding to a member pointer, we use a method pointer, right? Why does this not work? It's because unions can also have methods. So who knew in this room that unions could have methods? Because this is something I learned in a reflection talk. Yeah, I don't know why. I've never seen it before, but unions can have methods. So this doesn't work. So anybody who thought that who answered this question that they think you can reflect if something's a class or a struct type, you can't. It's not possible. The STL actually uses some internal compiler magic. There is something that's called std is class type. It can only be implemented. Either you have to implement is union type with magic or is class type with magic. So Clang's STL implements is union type with some internal compiler magic, and then you can write is class type by checking this and then checking that it's not a union. So yeah, crazy. Okay. Is it possible at compile time with only C++ compliant code to return the name of an enum value as a string at compile time? So imagine here this code down here. I have an enum called color, and it has a value red, and I want it at compile time to return the string red. Who thinks it's possible? Okay, one person. Who thinks it's definitely not possible? Okay, so you have a good intuition, right? Because when I saw this first, I said, it can't be possible. And why? Because when we're doing reflection, we're always using template meta, template meta programming. And so we're always using the type system, or abusing the type system to do reflection. Now, names of enums are not types, right? They're identifiers, and the names of identifiers don't really go into our type system. And there is a caveat here, because it is possible, but it's implementation dependent. So it's implementation defined behavior, but it is possible. And the trick is std source location function name. Okay, C++ 20 std source location function name. And why does this work? we're going to create a function called enumName, which takes a non-type template parameter, which will be our enum value. Now, as we know how template functions work, every time you use enumName with a different enum value, the compiler needs to create a new function. And function name should be unique, right? So what does this thing print out here? For example, on clang, it prints out the name of the function, but then also tells you what the enum value is. And it conveniently puts red in there. And so with a bit of compile time string manipulation magic, you can get this to just print out red. Don't do this at home. Different compiler versions even will, that string that it prints out will be different. MSVC doesn't have a source location function name yet. In fact, only the very, very newest Clang version has function name. So for all the Clang versions, there's __ pretty function, which does the same thing. And for MSVC, use funcsig, which does the same thing. And don't ever implement this yourself. Daniel Gonkarov, I hope I'm pronouncing his name correctly, created this library called Magic Enum, which honestly, this is the best library. I use this on every project. It's the first non-STL library I include in every project. And because it also does the reverse, it can convert strings to enum values. It can even iterate through enum values of an enum, all at compile time. It's single header. Yeah, definitely go check it out. And he figured this out, right? So, okay, now we come to the holy grail part of this talk. Is it possible to reflect on names and types, both names and types, of members of a POD class struct? POD is not really correct anymore with new standards, so we can, if we're a C++ 17 and beyond, we would say aggregate class type. But when I was talking to people, most people were more familiar with the term POD, so plain old data. So who thinks in this room that it's possible to reflect on names and types of members of a POD class struct? Okay. Okay, let's leave that unspecified for a moment because we're going to actually put this into sub-questions, okay? And there we can answer this more. Can we count the number of members in a struct with pure C++, only standard compliant code? So yeah, okay. And yes, we can. And we're going to use SFINAE again, but let me just make this a bit simpler for me. And then we'll relax some assumptions. So first, instead of counting the number of members of a struct, we're going to check if a struct has at least n members, right? And then we're going to limit the struct to only have integral type members, which we're going to relax both of them. But let's just assume that we have a struct like this that only has integral type members. We're going to use this check expression thing. Before this check expression only involved an expression with t. Now it's also going to involve this non-type template parameter pack that goes from 0 to n-1. What is n? N is, right, we're trying to write has at least n members. So if we're trying to check if it has at least 5 members, n would be 5, and our template parameter pack would be 0, 1, 2, 3, 4. Okay? And now we need to check an expression that is only well-formed if our struct has at least 5 members, and that expression will involve t and 0, 1, 2, 3, 4. Anybody, any idea what you could do?
You just initialize it.
Exactly. So we are just going to initialize this thing with an aggregate initialization. And right, if this thing only had 3 members, the struct, then there would be excess elements here. And so it would be ill-formed. The compiler would ignore that overload and would only use the false type. So we know, oh, it doesn't have at least 5 because it only had 3. If it has enough members, then that initialization is well-formed and the compiler accepts it. And if you replace the parameter pack back in, it looks like this, right? Okay, so let's just zoom into this bit of code here. I don't want to keep on rewriting all of this other stuff, so let's just zoom in. Let's just take this thing and put it on a separate slide. We had a struct which is only integral types. Now let's say the struct has pointer types. So how do we fix this? This would be ill-formed now because our parameter pack would be 0, 1, 2, 3, 4. We can't initialize char with 5. That would be ill-formed. So how do we fix this? Well, we use the comma operator. Comma operator is really neat because this thing is still expanded. but only the last element will actually be used in the aggregate initialization. So only null putter will be used in the aggregate initialization. So that's really useful. That's how we could expand it to pointers. How can we expand it to any type? We introduce a new struct called any, which has an implicit conversion operator. And that implicit conversion operator is templated so it can convert to any type implicitly. So it's like this magic thing. So we just replace that null putter with any, and now this works for any struct. Right here, it would have to be constructible, but like I'm restricting this to POD types. You can do lesser restrictions, but then you would need more tricks. So I'm doing the simple version here. Okay. So yeah, that's that any trick. So we're not quite there yet, right? We want to count the number of members. We have now implemented has at least n members. So we create a const expr recursive function. It starts out at I equals 1. We first check, does it have at least one member? If it does, we check, does it have at least 2 members? And if it doesn't have 2 members, then it must have had 1 member, right? So we did it. We counted the number of members in a struct with pure C++ standard compliant without using the STL. So it can be done. Now, second sub-question, can we get the type of a struct's members? So we got the number of members in a struct. Can we get their types? Yeah. Yeah, we can. Yeah. And what's the magic keyword we need to use? What's the reflection technique? New C++ features, C++ 20, I think, or 17. I'm not sure. It's. I know an older way. Okay. So let me just rephrase this question just to make it a bit more clear. Like, okay, we want to get the types of a struct's members. Let's just say we want to convert a struct to a std tuple. So, right, so where the elements of the tuple are the member types of a struct. It just makes it a bit easier in the slides that are going to follow. So we want to create a struct to tuple function, right? It takes a struct S, and then it spits out a std tuple where each element corresponds to the member type of that struct. And yeah, the magic thing we're going to use is structured bindings. So if we would have exactly 5 members, this is how you would do it, right? We would just introduce A, B, C, D, E, and then we create a tuple with that. So it's actually really, really simple. The problem is there's no way to generalize this to any number of members. So this is explicitly for 5, and the reason why it's so hard is structured bindings are not normal C++ code. It's just a list of new names that you're going to assign to new variables. So the compiler treats that as a list of identifier names. So you can't put in normal C++ expressions. You can't put in parameter packs. So what we need to do is we need to create a helper function, make this a helper function, and then create several overloads, copy and pasting this thing as many times as we think there might be members. So I made it, I did it for 1 here, you would have to do it for 2, 3, 4, and then you create a little wrapper function, which calls the right overload depending on how many members you counted. Now this could change in C++ 26, I think. There's a proposal to allow structured bindings to allow parameter pack expansions in structured bindings. So that would fix this. But is there another way to do this without copy pasting? There is, and it has some other downsides, but there's a way to do this without copy pasting at all. And for this, I'm just going to show this little my struct thing that we want to reflect on. And then we want to create a function called reflect struct. It takes 1 template argument, which is the struct that we want to reflect on. So in this case, it would be my struct. And then it takes a lambda as an argument, which has a templated lambda. And the type of that argument there, that underscore argument, will then be the tuple that represents our struct. Okay, so this is what we want to implement. We have our reflect struct function that takes a template argument, which is my struct. It calls that lambda with a tuple that represents the members of that struct. This is not quite correct yet because the lambda needs to pass in a value. So we're actually going to pass in an instance of that tuple. We don't really want that, right? We just want a type basically passed in there. So instead of passing in a tuple, we're going to pass in a std type identity of that, which is an empty struct, which just has a type alias inside called type, which we then could use. So this code, for example, would just print out, std tuple in string bool float. So this is the thing we want to implement, reflex struct. How can we do this with pure C++? We're going to use the same trick as before. We're going to do aggregate initialization, but we're actually only going to initialize the very first member. And we're going to initialize the very first member with the same any class that we did before. So we have our any class here, and we have our implicit conversion operator just as before. And now we're just going to add some template parameters to this any. So first we're going to add the struct that we're trying to reflect on, which is t. Then we're going to add a lambda because we want to pass in this lambda into the any, because we're going to need that later on. Then we're going to add a recursion parameter I, which starts off with the number of members that we have. And then we're going to add variadic template arguments to this thing, which is u, which are the already deduced types of the struct, which right now, if you look down here, we don't know any types yet, so u will be an empty pack. So when we get to here, we now know one member type, the very first one, right? Because this thing, we're aggregate initializing the very first member type, so v will now be the very first member type, and so we recursively do the same thing again. We aggregate initialize. We now know the first member types, which is u by definition, right? Those are the ones we already resolved. We now know one more, which is v. Now we recursively call any again. We pass in t and lambda again. We decrement the recursion count. And now what is u? Well, u is the past u's that we've had, the ones that we already know, but we know one more now, which is v, right? We found out one more. So the second time we go around, u will be something now, we know another v, and then we're going to try to get the third member, and so on, right? Until I equals 1, until our recursion non-type template parameter is 1. There we create a specialization of any, because here for this last one, the conversion operator will be called one last time for the last member. And now we know all of the types because they are now u, all the ones we deduced before, and then the last one v, and now we can call our lambda. So this is how you can do it in pure C++ code. It has one huge downside, though, is that it's not very flexible because there's no way we can get the type outside of that lambda. So the lambda is called with that type, but we can never, ever return it. Right? What we would really like to do is to make the return type be dependent on that template parameter, which you can do with normal C++, and we could get the return type outside of this lambda, but then we can't do anything with it because the return type of this conversion operator is fixed. It has to be v. So this works, but it has a huge restriction. Right? And so the structured binding thing is actually better. There is a way to get this out with older C++ standards. There was actually a defect in the C++ standard which allowed you to use friends as a sort of state in the compilation. It was really, really crazy because, the type system should never be stateful, but it was by mistake. So there was a way to get it out with previous C++ versions, not anymore. But this was just a glance of what, this was a really, really quick run-through of how this works. This talk does it in much more detail, and all of the things I didn't talk about, like what if there's a bit field inside. Anthony Polukin covers all of this. And there's a library called Magic Get or Boost. It's actually in Boost PFR, which does exactly that. You can convert a tuple, a struct into a tuple, and the other way around. So definitely recommend that library. Very, very useful. Okay, can we get the struct names? Who thinks we can? Okay, this is a bit of a bad question because it's Clang only and it's using a really bad trick, but it's possible. In the newest versions of Clang, there's something called built-in dump struct. So this is no longer C++ compliant code. You give it a pointer to a struct and a lambda, which has the same semantics as printf. And what this thing would print out is this thing here, and it includes the names of the members. And the thing is, I've tried this. If the lambda is const expr, the whole built-in dump struct is also const expr. And I've tried this. You can actually really get out the member names all at compile time. So yeah, you can use it, but I think it's only on Clang trunk right now. So, but it's possible. Okay, last questions, and this is not a serious one. Can you check if the author is using tabs or spaces at compile time? So, what?
With pre-compressing? Can you define tabs to be something else?
No. Okay. The trick is std source location column. So we put the std source location column one tab indented, and if that thing, so column counts from 1. It's not 0 based. So the very first character is at index 1, and so if you have a tab, it would be at index 2. The problem with column is that only Clang trunk implements it yet, but I found another way to do this, which is even more fun. What if we don't have std source location at all? So we don't even have function name. I said before that we have this pretty function macro, which does exactly the same thing. So this will give us the function name. It's templated, so we have the same thing again for every version of func name. It will tell us which template argument we have. But what if we give it the decal type of a lambda? And the nice thing is that GCC and Clang, they print out this. Lambda at file.cpp line column number. So you can get the column number right now with even pretty old Clang versions by using this trick here, by just figuring out the function name. And so the full code looks something like this. Column number of lambda definition. You do some processing of that string to give you the column number. And then you write, is using tabs, column number of lambda definition. And you have to make sure that that lambda is exactly one tab indented. And if that gives you 1, then you're using tabs. And if not, then you're using spaces. And if you want to find a gold version of that, it's right there. Yeah, so that concludes my talk. Thank you very much. Time for questions? Yeah.
What are the compile times?
I don't know. I didn't really benchmark them. I mean, it didn't seem long, but yeah. Timur.
Yeah. Sorry if this is a nasty question.
Yeah.
Anyway, thanks for the talk. It was awesome. It just occurred to me. If you go back to 5.1, the thing where you were like seeing if you can initialize an aggregate with like not more than n arguments.
Right, yep.
It just occurred to me, doesn't this fall apart as soon as you have a member of an aggregate which is itself an aggregate? Because then you have brace elision, and then you can actually initialize an aggregate with more initializers than the number of members it has.
Yeah, so Anthony Pelucan, he talks about that there. I mean, it gets very complicated and meta, but you can, because you can figure out there is in the SDL something that's called is class or struct type. So you can figure out if you are initializing something to a class or a struct type with this any, right? So this any, we know which type it is. We can then check at compile time if it is a class or a struct type, and then we now recursively count the members of that struct type first. So we know how many members that struct type has to have. And if that struct type has other structs in there, we have to count those first. So it's like kind of nested, right? So that's why I said I glossed over a lot of details here, but it is possible, yeah. It's very, very hard. So I mean, Anthony Pelucan goes through that in his talk, and it gets extremely difficult, yeah. Any other questions? Okay, thank you.